Okay, now it's recording. So we start with this theorem. If we have two independent random variables and we take their sum, then the moment generating function is the product of the moment generating functions of these. And this hinges on the idea that it's independent. The proof is very simple. If we take the moment generating function of y, it's the expected value of the e to the t y, which is e to the t times x1 plus x2. Well, there's a missing parenthesis. I'm not going to fix that now. This is e to the t x1 times e to the t x2. Now, this is the expected value. And here, x1 and x2 are independent. So any function of x1 and x2 are independent too. So the expected value of the product is the product of the expected values, but these expected values respectively are the moment generating functions of x1 and x2. So this is a theorem that I wanted to state here is because, you know, very often the case we can rely on this idea as well, so that we get the moment generating functions. I'm not going to go through in detail of the proofs, but most of the proofs that we are going to deal with when we take a sample and we have an independent sample, we are adding these together. Most of the results that we get can be proved easily by invoking this, that the sample, we just multiply the moment generating functions, and most of the results can be proven with this. But we're not going to go in deep detail here. This is for those of you who are more interested in looking into the theory more deeply. So here's an example. If we have a binomially distributed variables x and y, where they have the same p, but the different number of repetitions. So they grounded on a Bernoulli experiment of the same probability. And we conduct one calculation, we carry out x and it's repeated n times, and we carry out y, which involves repeating it m times. And then we calculate the moment generating function of x plus y. We get moment generating function of x times the moment generating function of y. And the moment generating function of binomial distribution looks like this. We already proved that. And when we multiply these together, we notice that the exponent changes into n plus 1. So this is the moment generating function of a binomially distributed variable with n plus m repetitions and p probability. So it's not surprising when you think about it. If you do a binomial distribution, it's repeat a Bernoulli experiment p times, calculate the number of, n times and calculate the number of successes. Do the same Bernoulli experiment m times, calculate the number of successes, and then you add them together. It's the same as doing the experiment n plus m times and adding those successes together. So it's not surprising. But this is a sort of example of the way we can use this to prove certain things about distributions. So we'll have some exercises where you prove certain properties of these distributions when you add them together. So the random sample often involves adding values together. And if you calculate the sample mean, which we already talked about, add the values together and divide by n. So this gives you tools to do that. Important corollary here is that if we have some number n of normally distributed, here's a problem I really do need to fix. If we have it's missing a parenthesis there. Sorry, a comma over there. Since the reason why I have more typos now than before, when I was working from, I did have a lot of typos then, but they're even more now. One of the reasons is that I have a different editor and it's got a different set of shortcuts. So I'm really bad at typing, so I often omit some keystrokes. So if you add together normally distributed variables with known expected values and variances, then the expected value of the resulting variable is still normally distributed with an expected value, which is the linear combination of the expected values. and the quadratic linear combination of the variances is the variance. So this is proof is rather straightforward application of the moment generating function. I'm not going to go there. We derived the moment generating function of the normal distribution. It's somewhat involved in algebra. Don't see a lot of point in there, but you have the idea that you can prove it using the moment generating function, and that's all we need to know here. It's very important to understand now that any linear combination of normally distributed variables is normally distributed, and that you can then calculate the expected value and variance easily from the variances and expected values. But they have to be independent. If they're not independent, there is a way, which is not a matter that we discuss in this course, but if they're not independent, then they have covariances. So the covariance, if they're independent, then the covariance is 0. If they're normally distributed and their covariance is 0, then they're independent. We can assume that. I think I'm not going to claim that we can assume that they are independent if they're covariances, but let's say that we have a situation where they have only linear dependencies. If they have only linear dependencies which are captured by covariances, then there is a way of using linear algebra to then come up with a linear combination of those expected values and variances. So it's a little bit more involved. It's not straightforward adding. There's some matrix algebra involved, but that's a more advanced course topic there. Just know that for normal distributions, you can do a lot of things that you can't do with other distributions. And that's one of the reasons why the normal distribution is so, how should I say, appealing. Appealing is probably the word. I mean, it's a little bit treacherous as well, because the mathematical niceties of normal distributions make it appealing, but it can give us a bit too optimistic analysis in many situations. I think I'll show some examples of that. So let's now consider a random variable x, and we take a sequence of random experiments, and there should be a slash there. So we take, we call this sequence of independent experiments, each having their own outcomes, a sample of x. So these are kind of, we can think of the random variable as we can split it into n different cases. In particular, we have the expected values and variances are the same as x. So the whole distributions are of each of these is the same distribution as the whole of x. And statistics from the sample, we say statistics are those parameters of the distribution, which, in fact, the statistics are certain formulas that we calculate from a sample that attempt to capture some feature of the distribution. So statistical analysis really is taking a random sample and then doing a certain set of computations on that sample. What is AI? Oh, sorry, there was a question I missed in that. Did you mean in here, this AI here? You asked it. This slide. Can you see this? This. You mean this one? Okay. So here, just to return to this. So we have here some random variables. We are combining them, each having a weight or some kind of a coefficient AI. We are adding these together, multiply xi with some real number AI. So this is what we call a linear combination of these. If you think about this AI, you can think of it as we have a vector, and we have a weight for each of these random variables. So we give, let's say we take twice your salary plus 2 times your, sorry, 1 times your weight minus 3 times your height. Let's assuming that these are independent. They're not independent probably, but let's assume. And then you calculate this linear combination here. That's a random variable which has normal distribution like this. And the expected value is 2 times the expected value of the first variable plus 1 time the second minus the expected value of the third one. And then the variance is the, 4 times the variance of the first one plus 1 times the variance of the second one plus 1 times the variance of the third one, because the coefficients were 2, 1, and minus 1. So the idea here is just that if you combine these, add them together, multiply them by some constant and add them together, then in fact, the new distribution you get is completely determined by very simple formulas from those. That's the role of this coefficient here. And someone asked me, can you explain this coefficient? But it's just any coefficient. So it just means that if you combine them with different weights, you still get normal distributions. And that can be proven from this theorem here. Right? Okay, good. Moving on. Sorry. So statistics, let's go. Oh, yes. How is that? That's good. Good point. Good point. Oh, thank you. Keep them coming. If you know there's some silica, you see, there was a saying with some of my friends, you should read not what I've actually written, but you should read what I mean. And that's good. Alex pointed out, I meant EXI equals EX, not equal to X. Yeah. Thanks. Please point these out as you see them. I have a lot of typos here. I don't necessarily notice them all. I try to make them visible. All right, let's move on to statistics. So we already defined this, but remember we talked about when you have an actual sample, meaning you have the numerical values. We call that the sample mean. But you have to actualize the realized value, which is the actual values you got, and then the random variable before, if you think about the random variable as before the fact. So it's going to be random before you have actually made the experiment of measuring or figuring out these n numbers. It's going to be a random variable. And once you have those numbers, then there's an actual value of the average of that particular outcome of the sample. And it's important to understand these two, it's the difference between rolling a die and the number that you actually got when you did roll the dice, right? You understand this difference. So we focus here, our analysis, of course, on this random variable now. This is a value simply by which you observe a certain outcome and then you just calculate the average. But you have to theoretically think about that these outcomes come from this random variable, which is simply the linear combination of those independent occurrences of that random variable x. So we define, given a random variable x and a sequence of random experiments, we define a new random variable, which is the average, add them together, divide by n, the sample mean. All right. And there's a theorem which we state here and has a very profound result. So the expected value of x, if it's mu and we have a random sample of that variable, then the sample mean's expected value is that same as the expected value of x. And what is more important, really much more important, is that the variance of this sample mean is the variance of x divided by n. So what does it mean? If you think about the variance, which this is a little bit of an abuse of terminology, but you can think of the variance as being the measure of how random a variable is. If the variance is large, then the numbers are scattered far and far around the actual expected value. When the variance is small, then they tend to cluster more closely towards the expected value. And this is a profound result, is that if you calculate the average, the sample mean, then the sample mean's expected value is there at the expected value of a single outcome. But the variance, when you take a larger and larger sample, the variance goes smaller, so that the distribution of this sample mean gets more and more compressed around the mean, or around the expected value. Here we see divided by n. And this is really a profound result. Let's prove it for the variance. I mean, the expected value is relatively simple, because we already know that the expected value is the sum of expected values, and then there's 1 over n. It's 1 over n over the sum of these. All have the mu. That's n times mu divided by n. So it's obviously the expected value of that is going to be mu. But let's look at the variance. So in the term of the variance, and here, yes. So effectively, what you mean is, you have to understand this. We're talking about the sample mean as a random variable. So the sample mean means that you take a bigger and bigger sample of your random variable, calculate the average of that. Then what it means is that average may twiggle and twitch around the expected value, but the larger the sample is, the less it varies around that expected value. So think about this. What is the expected value of rolling a dice? 6-sided dice. That's 3.5, right? So if you roll it once, you get a random value which has certain variance. I mean, it's the variance of something n squared minus 1 over 12. So that's that would be 30. That would be 35 over 12. The variance. That's somewhere around. That's somewhere around 3. So if we take the square root of 3, that's roughly the standard deviation. So on average, if you roll a die, yes, its expected value is 3.5, but you will more often get a 5 or a 2 than you get a 3.5. Well, obviously you don't get 3.5, you get 3 or 4. And it's not surprising. I mean, 3.5, there's 1, 2, 3 on the left-hand side, and 4, 5, 6 on the right-hand side. So, if you know it's going to be bigger, then on average, you're going to get a 5. And if you know it's going to be smaller, then on average, you're going to get a 2. But if you roll the die 100 times, you're still going to get on average the average of that 100. So you roll it 100 times, divide by 100. So that is going to be on average about 3.5. However, the variance is now the previous variance, which was about 3 roughly, divided by n, which was 100. So this is 3 over 100. I'm just approximating. It's about 1.6. Then the 1.7, the square root of that. But if you're dividing that variance by 100, so if you take the square root of that, it's 10. So you get about 0.17. So most of the averages of 100 die rolls will be between 3.3 and 3.7. You see? So while one die roll is on average, you'd expect it to be about 3.5, but most of the rolls will be between 2 and 5. That doesn't actually say a lot about that. But then if you take the 100 rolls take the average of those 100 rolls, you get about 3.5, and most of the cases will be between 3.3 and 3.7. So that's 100 rolls gives you, is more likely to give you a value that is closer to this expected value. That's what this theorem says. And you know easily the variance of the sum. There is a coefficient here, 1 over n, so that coefficient comes as quadratic here, and add the variances because they are independent. You can add the variances. So this is n times the variance of x, but you are dividing it by n squared. So it's this variance of x divided by n. It simply means that the larger the sample you have, the less variance the average will have. It converges towards, I mean, if n approaches infinity, this variance approaches 0, and then this mu approaches the actual expected value. Yeah, that well, good. that's the whole point of that slide. Good. Keep those questions coming. It's very. We'll use this theorem later to get what we know as the confidence interval of mu. So what we are aiming for is a theory that gives you some idea of probabilities, that how likely it is that you know some range in which the average is. When you take a sample, you don't know. You get an actual average, but you don't know how good an approximation that is. If you know the variance, then yeah, you can probably get a better idea. If you know the variance, then you can get a better idea. And we call that confidence interval, and I'll explain it to you probably tomorrow. Important corollary or consequence of this theorem is that if we have a normally distributed variable, then the sample average has or sample mean has a normal distribution, but with diminishing variance as n grows. So this is important. The next topic hinges on this. So we have the sample mean here, and this is a danger. This is what the central limit theorem is akin, which I explained to you. It's like those. Well, let me back it up down a little bit. Now, let me say it straight. It's like handing a loaded gun to kindergartners. What I mean is, you have to be really critical if you are going to apply the central limit theorem, and understand what the assumptions there are and when it applies and when it doesn't. And then, you know, you're going to use it anyway because everyone else is going to use it, but have to understand the nature of this theorem. There is a, I don't know if you know this, the so-called, I don't know how you pronounced it. It's called the Dunning-Kruger effect. I'm not sure if that's how you spell it, but it's roughly that, or is it Kruger with just U? It's the idea that if you know a little bit about some topic. Oh, sorry, I sent it to a private, sorry. This is, sorry. I didn't mean to send it privately. So it's called this, so it's the effect that if you know a little bit about the topic, then you will consider yourself an expert. And when your expertise grows, your certainty, your perceived certainty of the effect diminishes. You'll be less inclined to think that you know something for sure if you actually know more about the topic, and you'll be more inclined to speak with authority if you don't know a lot about it. And that's something that you guys need to be aware of, because if you know the central limit theorem, then you will, if you understand the central limit theorem and how it works, then you are more likely to actually apply it and apply it in places where it doesn't actually apply. Yeah. So let's stated. If X is any random variable with a known variance and expected value, and we define the standardized sample mean as we take the sample mean but subtract from it the mu and divide it by sigma over the square root of n, then this will be this so-called standardized sample mean will have a distribution that closely resembles the 0,1 normal distribution when n approaches infinity. And really, if you think about what that means, I mean, the expected value, you subtract the expected value and you divide by the standard deviation. If you look at this, you take this as a coefficient, calculate the variance of this. So I just write here. So the variance of I just write it like this, x, write it like this, x minus mu I'm going to call that S for sigma over S divided by, right, this. So what is that variance? You first take that, remember it's a random variable and it's got a multiplier, which is that 1 over S squared, square root of 1. So it becomes 1 over, so it becomes the square root of n divides the divisor. So it's actually a multiplier and S is a divisor. So we get, it becomes out as a multiplier, but becomes quadratic. You take it to the second power because it's inside the variance. Remember, a times x variance is a squared times the variance of x. So that multiplier, when we take it out, it becomes n over s squared times the variance of x minus mu, right? But x minus mu, that's the sample mean of x minus mu. Mu is a constant, so it doesn't have a variance, so it becomes n over s squared times, and remember the variance of the sample mean is s squared, I put the parentheses, s squared over n, right? So that is equal to 1. So it has a variance of 1. And the expected value, well, dividing that, if we subtract that, x from it, we take the expected value, it's 1 over this times the x expected value of x bar minus mu, but the expected value of x bar is mu, so that expected value is 0. So it's got an x0 expected value and variance of 1. And what happens is that if you take a larger and larger sample, then this normalized quantity will resemble, have a distribution that resembles the normal distribution, 0, 1 normal distribution, more and more. And most of the analysis in statistics will be hinging on this theorem, meaning that as n approaches infinity, this normalized variable has a normal distribution, and that means that we take a little bit of a leap, one that is dubious at best, of faith, saying that, okay, it holds when n approaches infinity, so when n is pretty large, we can assume that this variable is normally distributed. And that's not necessarily a good idea to think so. But most people do, and we'll work on that. So it's based on these assumptions. So it means that large samples will behave as though they are normally distributed. I mean, if we take the standardized means. In practice, this is applied so that we have a large sample, we can treat any estimates such as sample mean or add them together, or the sum of these as being normally distributed. And most of the tools in statistical analysis is based on this assumption. So it's a dangerous assumption to make, as it hinges on two very important assumptions. And can you spot those assumptions? I mean, I didn't mention them, but if we mentioned them, they're implicit in here when we are using the bar X here. One implicit assumption is that the sample average or sample mean has been actually gathered in such a way that all the occurrences of X in that sample mean are in fact independent. So for example, if a lot of psychology, a lot of the modern psychology, which makes use of, which used to make use of extensive statistical analysis in the 60s and 70s, even today, has been based on early work that was done on university campuses in the US. And the subjects in your experiments were mostly students. And even worse, they were mostly students of psychology. So you can see that if you measure some behavioral aspect, treat it as a random variable, and think about and assume that this random variable is, for instance, that it represents the population and the average is independent. The average of those is a random sample of independent individual variables from the whole population. Then you're already leaping into a lot of conclusions that are not going to be true. If it's analysis of someone's behavior and they've read the book written by the professor who has this hypothesis and who's pushed their agenda on their students, and the students have read that book and think, oh, this is the way humans behave, and then they are subjected to this experiment which measures whether people actually do behave in this way, and they come from they come from a similar socioeconomic background and whatnots and all that. It's not an independent sample. So that's why some of the early work is dubious at best, and even though they've carried out some statistical analysis there. Another important assumption is that the expected value in this case even exists. I mean, why do we assume that the expected value exists? We have encountered already distributions where the expected value doesn't even exist. If the expected value doesn't exist, then who are we to say that the actual value somehow exists in this case? Because I mean, everything here we assumed in all the parts here that we defined or everything that we proved, we assume simply that these variables have an expected value. Well, I'm not going to prove the central limit theorem because the proof is somewhat involved. You can check out there are different versions of the central limit theorem. This is the weaker version of the central limit theorem. It says that these are all independent and have the same expected value and the same variance. I'll show you a stronger version of this shortly. But whenever we are comfortable in making this assumption, I wrote here dot over the sign. So X pretty much follows the normal distribution. We say X is as good as normally distributed. This applies to certain large populations to the extent that it makes sense to use it often, but not. You can also read this as X. We calculate X as though it's normally distributed, but take these results with a grain of salt. it all hinges on this assumption of having a large enough sample and so forth. Here's an example. We have an elevator that is a warning that it can lift at most 25 persons or 2,000 kilograms. The weight of a single person is a random variable, and let's assume that the average weight of the person is 74 kilograms with a standard deviation of 10 kilograms, meaning the variance of 100 kilograms squared. What's the probability that 25 people weigh more than 2,000 kilograms? So it can fit 25 people. Let's say that there's enough oxygen for the elevator ride for 25 people, but it can move as long as those weigh less than 2,000 kilograms. So let's say that we assume that we are adding these together and calculating the normalized version. The normalized version would be x minus 74 over over 10 divided by the square root of 25. So that's 2. But then if that's 0, 1 normally distributed, then going in reverse, multiply that by the 100 and over 10 over 2, and add the expected value 74, then what you in fact get is a normally distributed variable with expected value of 25 times 74 and a variance of 25 times 100. Look, this is not the average. Alex asks a very good question. Just give me a second. Take off my hoodie because it's hot in here. What is the it depends on your distribution. If your we'll talk about the large enough sample for the central limit theorem. We'll talk about it shortly. If we have a good reason to believe that the underlying distribution is pretty much like normal distribution, then the n doesn't have to be very large. If we cannot assume this, if we know that the underlying distribution with expected value and variance can be something like the uniform distribution, or even more pathological, something that has two tails or weird shapes, then the sample should be larger, right? So if you have a symmetric, roughly bell-shaped curve for your distribution, then you can use the central limit theorem with a smaller n. But if it's a pathological distribution with a high skewness or bumps at the edges or something like this, then the sample should be much larger. I can't say much more about it. The usual rule of thumb in statistical analysis is people say that n has to be over 30 unless it's already normally distributed. That's roughly how they say. I'm not a fan of these rules of thumb. I'm more of a fan of doing some rudimentary analysis of checking for whether or not it makes sense to use the central limit theorem. For instance, this goes way to more advanced statistical analysis. That's a good question. Is there a formula or guideline to determine whether someone should or shouldn't use this theorem? It's a bit beyond the scope of this course. There are certain ways of checking whether the distribution is in fact normal or pretty close to normal. One way to do this is to look at the underlying variable, calculate certain features of that, and such as kurtosis or skewness, which are the higher momentums. And if those are, the proportionate numbers of those are pretty close to normal distribution, then it's safer to use the central limit theorem. And if they are very far from those proportions that you would have in a normal distribution, then you should have a larger sample or refrain from using the central limit theorem. This is, of course, a little bit, you know, like I said, it's beyond the scope, and if you study statistical analysis a little bit more, you should understand it. Also, you know, if the underlying variables are Bernoulli variables, and then you derive so that there are, you know, 0, 1 outcomes, you know, dead, not dead, something like this. And then you're calculating a very large N with binomial distribution. We'll see shortly that if that probability of the Bernoulli event is relatively large, but not too large, somewhere in the region of 0.5, not very close to 0, not very close to 1, then the binomial distribution very quickly with not very, you don't read the very large N for the binomial distribution to start resembling the normal distribution. So those are situations where the normal distribution works pretty well. But then if you take things like people's income, you very quickly notice that it's more of an exponential distribution, so that, you know, there's those tail events, you know, billionaires are far more common than you would expect if it were a normal distribution. Even if the number of zeros in your paycheck would be assumed normally distributed, it would still not resemble the actual income distribution in the world, at least. But this is a bit beyond the scope. I'm just saying here, I'm giving you this theorem so that, you know, we can apply it here, and we will apply it, and I expect you to learn to apply it. But just understand that if you're going to apply it in a real world situation, understand that you're not going to get the level of certainty that this mathematical tools seem to imply. That's what I just want. I don't want to scare you too much about this. I don't want you to be scared of using this. I just want you to understand that it has limits. It's a very powerful theorem and it's easily misapplied, but, you know, if you have no other tools, apply it and then understand that what you get may be wrong. That's my advice. It is. There's a possibility of getting a level of confidence in this theorem, but those tools of analysis are beyond the scope of this theorem. So it's really, it's the higher the momenta and estimating the probability of 5 sigma events, for instance. 5 sigma event meaning that it's 5 times the standard deviation. That in normal distribution, the 5 times standard deviation events that have probability, you know, that are further away from the mean than 5 times the standard deviation, those should be exceedingly rare if the underlying distribution is normal. If it's not normal, they may occur much more frequently, but if it's a normal distribution, then most definitely you should not have those events. So if you have the number of 4 sigma, 3 sigma, 2 sigma events roughly similar to what you would expect in a normal distribution, then it's pretty safe to use that. But, you know, you might still get that 8 sigma event, which should be all but impossible with the. So yeah, this is, remember, there's always a risk with randomness that certain things might happen even though they have a very, very low probability. But it is possible to not to determine, but raise the level of confidence by more advanced tools. But remember, any model or theory that you apply to the real world is only as good as the assumptions upon which they are made. Oh, sorry. So if you make assumptions that are wrong, then your model, well, who knows? It might be right, even though the assumptions are wrong. I mean, they may still work. Let's calculate this. So we get here, so that's the sum of 25 independent variables with 74 expected value and 100 variance. And we get this variance here, this expected value and variance here. Now, we use this normal distribution as our approximation of the total weight of 25 random people. And why this is 25 times 100, you know, it's each of them has a 100 variance. We have 25 of them, so you add them together, so it's 25. Remember that if this was one variable and then value times 25, then this multiplier would be 25 to the power of 2. But because this is 25 independent variables, then this is 25 times 100, right? This is a sum of 25 independent variables, each of them having a 74 expected value and 100 variance. So we look at the probability of x being greater than 200. So it's the probability of 1 minus x being smaller than or equal to 2,000, x larger than 2,000. So 1 minus smaller than or equal to 2,000. 1 minus probability. Now we subtract this expected value 1,850 and divide by the square root of 2,500. So in fact, what we're doing here, this is now the normalized. Notice that this is now the normalized variable. We subtract the expected value, divide by the square root of the variance. And we have to do the same to the 2,000, although this becomes what, 150 over the square root of 2,500. And that's roughly equal, well, that amounts to, does that amount to 3? 25 times, that's over 5. 25 over 1, that's 10, 50 over 50. That's 150 over 50, that's 3. Yeah, so that's the cumulative distribution function of the normal N01 normal distribution. So that's 1 minus the distribution at 3. We look it up from the table or we calculate it from a software, and we get 0.0013. So it has a probability of 0.13%. So in 13 cases out of 10,000, the total weight will be more than 2,000. Okay, this seems like a reasonable idea. Let's criticize this example a little bit. This makes sense if these people all arrive independently and randomly. But what if this is a hotel that hosts certain conferences? Okay, most conferences will have people who weigh just about average. They're just normal random samples. So, you know, the hosts conferences, and let's say for argument's sake that otherwise the hotel is completely vacant, but every weekend there is a conference and the conference guests are staying at this hotel, and after dinner they go upstairs and use the elevator. Okay, you understand what I'm saying? Now, most conferences will have attending a conference has no dependency on the weight. But let's say there's one weekend during the year, what happens is there's a National Bodybuilders Association has a conference. They're staying at this hotel. Do you think then that this 25 bodybuilders who are going to go into this elevator will represent a random sample of independently chosen people from the general population? You probably wouldn't. So I would expect that competitive bodybuilders' body weight average or expected value is far beyond 74 kilograms. Usually it is. Heavyweights weigh upwards from 140 kilograms. Or let's say it's what other topic would be? Maybe they're I don't know, power lifters. I mean, or yes, I mean, I don't want to be rude here, and I don't want to result in cheap quibs to any nationalities. But let's say they're Americans. That is true. I mean, if you look at yeah, I'm not true, but yeah, obesity is more common there. On the other hand, let's do this. Let's do it so that what if they are, well, what if this is somewhere in Asia, right? Asian people are usually somewhat smaller stature than Europeans or Americans, right? Maybe what if there's Samoans? Yeah, World Anorexia Conference. That's true, right? Or you know, I don't know, people who are suffering from stomach cancer. You know, what I'm saying is, your model is as good as your assumptions, and here we assume that it's a completely random representation of independent individuals from the whole population with this expected value and this variance. But if that assumption is broken, then obviously this idea doesn't work. Right. Let's move on. Here's another example. Let's say that we have a random variable and we know the variance and unknown expected value. So we know the variance is 25, and we take a sample of 50 n. Let's assume now that some assumptions are such that n equals 50 is large enough. Like I said, it's often the rule of thumb that is used is if that n is larger than 30, then your sample is large enough to use the central limit theorem. And let's go with that, but understand that that's a rule of thumb and it's not a hard rule that always applies, okay? So we can agree that we can always assume that if n is larger than 30, or if the underlying variable can be assumed to be more or less normally distributed already, then we can use the central limit theorem. Otherwise, we have to be careful. So we take n equal 50, and let's assume that this is a large enough sample. What is the probability that the sample mean differs from this mu by less than 2? So look, we get some sample mean, and we are looking for our confidence in the idea that we are pretty close to the sample mean. The sample mean is pretty close to the expected value. And if we know the variance, we can do it like this. So we look at the probability that the sample means and the difference between the sample mean and the actual expected value is smaller than 2. We don't know what this mu is. We're just looking for certain interval here. So the probability is the same as this x minus, the x bar minus mu is between -2 and 2. And then we divide by the sigma over the square root of n to get the normal. Now here emerges the normalized x. And if we punch in the numbers, the square root of 25, that's a 5, and n is 50. So we take the square root of these, this proportion, that's 1 over 2. So the square root of that is 1 over the square root of 2. So this probability mass here is between, let me just draw you a picture again. So if we assume this to be normally distributed, the normal distribution looks something, I'm sorry about my bad drawing, but normal distribution looks something like this. It's supposed to be symmetric, don't laugh. And the first value, which is 2 over 1 over the square root of 2, so that's 2 times the square root of 2, isn't it? That's 2 times the square root of 2. Yeah, that's about 3 or so. Yeah. So a little bit under, as 2.83 or so. So we have here the limits, this and that, and we are looking for the probability that we are in between them. So that region is so we get that, look, everything in here is this this latter part here, and then everything in here is this from which we subtract. So when we subtract from this region, we subtract this smaller region, we get this middle region. And by symmetry, this is 1 minus that, so we get 2 times that minus 1, and we get that it's 0.995. So that's 99.5% probability that this is as far as we are from the expected value. We're using the central limit theorem here, assuming that this is roughly 0.1 normally distributed. So we're getting close here. This is we're actually calculating now 0.5% confidence interval. This means that we're actually calculating that in 99.5% of the cases, we are within 2 steps, within 2 units of the expected value when we take this sample mean of 50 with this variance. Of course, it depends on the variance and the sample size because it's the divisor here. So the larger the variance, and then the wider this region is, and the smaller the n, the wider. So, and the bigger the n, the narrower this is. So the central limit theorem is a very wide-ranging, and we can consider some particular applications. I'm going to just discuss some particular situations where the central limit theorem applies pretty well. Here's an example. One example is the binomial distribution. We have n Bernoulli distributed variables. So these have 0, 1 outcomes and probability p. So you would expect the binomial distribution for a large n, if you normalize it, so you subtract n minus, take a binomial distributed variable, subtract n times b, p, and divide that by the square root of n times p times 1 minus p, then what you get is roughly a 0, 1 normally distributed variable. if n is large and p is not too large or too small, then this will roughly resemble, the binomially distributed variable will actually roughly resemble a normally distributed variable with expected value np and variance, which is the variance of binomial distribution np times 1 minus p. So it should be noted here that this applies for relatively large n and p that is in the middle range. Remember that if n is very large and p is very small, then it actually doesn't resemble the normal distribution. It resembles the Poisson distribution. So when the p remains constant at the middle and n grows large, then the distribution will resemble a normal distribution. But if p is very, 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 very small and n grows large, then it will resemble the Poisson distribution. So remember this difference between the two. In this normal distribution approximation, the p remains fixed and n grows. And then we normalize it by subtracting np and dividing by the estimate of the variance and so forth. So we get a 0, 1 normally distributed, which then, or we retain it like this. The expected value escapes because n grows and p remains fixed. So the expected value is large, and then the variance is also pretty large. A rule of thumb is that if both n times p and n times 1 minus p are, if both of these are macroscopic, let's say both of these are larger than 5, then the approximation is relatively useful. This means, I mean, why 5 is because this starts, when this happens and you start resembling the normal distribution, then the 5 sigma events, they become pretty rare. But this is just a rule of thumb and not a hard truth of any sort. But binomial distribution is, at least it's a relatively well-behaved one that gives us a pretty good normal approximation under these assumptions, of course. When we are approximating, and I see we are again missing here some parentheses. Let me fix that. Also, there's a especially and not especially. Seems I made some typos here. There you go. And there you have it. Now it's better. Especially for relatively small n, the discrete nature of a binomial distribution needs to be accounted for, because, and if you think about it, binomial distribution is a discrete distribution. So for fixed numbers, the probability of np and so forth, that'll be, it should be cut off at 3.5 and not at 3. I mean, here we have the cases x equal 1, 2, and 3. So we should attribute it to the probability, the probability of all those cases where it's smaller than or equal to 3.5. Anything that would round, when rounded, would result in 3 or smaller. And similarly, you know, if it's smaller than 2, then it's in fact smaller than 3, then it's in fact smaller than or equal to 2. So in this case, it's 2.5. So whereas in normal distributions, x smaller than 3 and x smaller than or equal to 3 are the same, in the binomial distribution, these are definitely not the same. There is a case there, and even for a relatively large n, those values that are close to n times p, meaning close to the peak of that distribution, then those values tend to have pretty large contribution to the whole probability, so that if you make the mistake of thinking this x smaller than 3 and x smaller than or equal to 3 are the same, then you have run the risk of having too much of error in your approximation. So you should approximate it to those values that actually round to, when rounded, result in the values that you are actually dealing with. And when rounding upwards, the same thing. All right, this clear? Good. Here's an example, which again is missing a parenthesis. Man, I am really bad with those parentheses, am I? Aren't I? You say, aren't I? Am I not? There. All right. So the probability, coin is tossed 900 times. So the coin has a probability of landing heads of 0.5 and tails 0.5. We make a quick sanity check. 900 times P is 450, and 900 times 1 minus P is 450. So we're good. This is definitely going to be very closely normally distributed. We take a normal distribution approximation of 450 and 225. 225, we calculate P times 1 minus P times N. In this case, N is 900. Is that correct? 225. That would be 450 P 0.5 times 900. That's 450 times 0.5. That's 225. Yeah, that's correct. So that's 900 times 1/2 times 1/2. We calculate the probability of getting heads greater than 495. So 45, an excess of 45, so 10%, if you will, a 10% excess of heads. Look, we expect 450 heads. What is the probability that there is a 10% excess of heads, meaning 495 or more? So we calculate this. And we're going to calculate this, and we're going to put this into the normal approximation so that we subtract the expected value and divide by the square root of the variance. And what we get is, this comes out at 3.03. 1 minus 3.03, that's 0.0012. So that's, again, 12 in 10,000. So it's not very likely that you get a very many heads, more than. So you notice that in this case, most of the head count will be within 10% range of the expected value, right? So about 24 in 10,000, so that's 2.5 in 1,000 cases will have a head count that is more or less than 10% so more than 10% off from the expected value. So plus or minus 10%. That's pretty rare. Most of the probability mass is centered around the top 10% at the middle. Not top 10, but the more common. No, look, let's go to this. I'll put some examples here. Why we are doing this is that because let's go take it back to that one that we had this. Remember that we are dealing with, what we want here is we want the normalized. This needs to be the same as the normalized version, right? So let's derive that normalized version, right? I'm going to write it here on the chat. So the normalized version here would be, I'm going to use this again, this for the, that's 1 over n times, you know, x1, you know, so this is what I'm actually doing. So I'm calculating the average of this. These x1s are the coin tosses. So we have 900 coin tosses. We are the coin toss average has a 0.5, doesn't it? Right? So I'm calculating the normal variable x minus 0.5 over the variance, the variance here being 0.5 squared and then I have to put here divided by the square root of 900, right? This is what I'm actually doing. Okay. However, you can verify that this is in fact the same as this x, which is I'm now going to calculate this in another way. We'll take the number of heads. So the number of heads, which is I'm going to call it y. I'm actually, this was wrong to use the hat x here, but I'm going to call this y, just renaming it. So y is actually the x1 plus and so forth plus x 900, right? That's my y. So y is in fact hat x times 900. Right? That's the y there. And hang on, I'm getting some weird messages. I have to shut down one of the windows so that I don't get those messages. So if we calculate it for this y, then we're calculating it for this y, which is here, it's called x, sorry about that. And when we do the same calculation, we subtract the expected value, then it's y minus 450 is the expected value. And we divide it by the square root of the variance, which is the square root of, sorry, I had a mistake there, that the divisor should be the square root of the 0.5 to the 2. So the square root of one variable, which has 225 divided by 1. You see, I'm having just one sample here, but it's got 450. In that was wrong. That second line that I had, it had a mistake. It should be this. It should have that square root from there, right? So. So we're really doing the same thing, but we can kind of jump a little bit. We can jump by directly subtracting we don't have to divide this by subtract the 450 and divide by 220, the square root of 225. Then we get the 0, 1 normally distributed variable here. I'll put some examples for Friday, and I'll show you that this is the same thing. So that the normalized has 0 when we're this is after normalization. Subtract the expected value, divide by the standard deviation, which is a square root of the variance. And this has a 0, 1 distribution, and we're now calculating this from the cumulative distribution function of the 0, 1 distribution. So this is the tail probability of those in excess of 495. All right. I'll show you a lot of these examples on Friday, so let's carry on. So there's one note about the central limit theorem. In fact, the central limit theorem can be proven even for the following. I mean, we had the central limit theorem had we had identical variables x1 to xn, and we had a sample of the same variable. And if we sample the same variable many times over, we get normal distribution for the sample mean. However, this even works for variables that are not in and of themselves samples of the same variable. If we have an infinite sequence of independent random variables, in fact, there is an even stronger version, even more general version, which says that we have an infinite sequence of random variables such that each of them is independent of an infinite number of the other variables. So they don't all have to be independent as long as the infinite number of them are independent of each other, and that there is certain, barring certain pathologies there. I don't remember the exact formulation, but let's for now assume that they are all independent, of which we know that only the expected values, each has an expected value of themselves. They can be different. They don't have to be the same. They're just called mu I and sigma I squared. And we need some rather general assumptions, ones that, for instance, this is not pathological. For example, it's not pathological in the sense that these expected values converge towards 0 in such a way that the sum of the variances is somehow, sum of the expected values converges to some limit, or that the sum of variances converges to some limit. So we assume that these are not, variables that approach a constant somewhere or something like this in a pathological way. So we define this yn as the sum of all these independent random variables, not all of them, but the first n of them. And the expected value is, of course, the sum of the expected values of those first n variables. The variance is the sum of the squares of these variances. So with rather general assumptions, meaning that no pathological dependencies are not diminishing in a certain way to 0 and so forth, when we mark this y star n, which is yn minus mu yn, so the expected value, we normalize this, then this normalized variable also approaches the 0, 1 distribution. To be perfectly clear, what do we mean by the approaching the distribution? It means that the probability that is associated with the cumulative distribution function of this, they will be very closely approximated point by point by the N01 distribution's cumulative distribution function. That's what happens. What we say that the probabilities related to these events will be more and more closely the same probabilities as the events resulting from the N01 distribution. Now we go to statistics. I can't quit yet because I don't know how much, we have a lot of stuff that I need to talk about tomorrow. So that I'm not going to stop until we are at Q2. So I'm going to just keep on going. We're going to stop abruptly shortly. Remember the sample variance. In the sample variance, we have this 1 over n minus 1 plus then the sum of squares of differences between xi and the average or the sample mean. So we define this as the sample variance and distinguish this from the actual realized sample variance. When we have a particular sample and we calculate, this is a real number based on this actual sample, and this is a random variable that before the fact we define. This is a formula that we then later apply to that random variable. So this is in itself a random variable. So the sample variance behaves, mathematically speaking, a little bit differently, as you would expect. For example, there's a square there, so it can never be negative. So obviously, it's going to have a different kind of a distribution. It's going to be very hard to look at what it is. Luckily, we have the theoretical tools, not quite as elegant as normal distribution, but they are closely resembled to the normal distribution, and we'll see that shortly, or closely related to, sorry, not resembling. So first of all, the important part here is that if we have a random sample of a variable x, the sample variance is an unbiased estimate of this variance of x. And by unbiased estimate, we mean that the expected value of this random variable is the variance. It's harder to talk about the variance of the sample variance. We'll talk about it a little bit, but not. We will derive a distribution for it. But for now, let's prove that unbiased estimate means that if we calculate a statistic from a random variable and we claim that we are going to use this in place of some parameter, then we say that it's an unbiased estimate if its expected value is the same. So for instance, the sample mean is an unbiased estimate of the expected value because it has the expected value that is the expected value. So you would expect it to resemble the expected value pretty closely, and it has other nice properties, such as we take a larger and larger sample, the variance grows smaller and becomes closer and closer, starts resembling the expected value. So we will derive a similar theory for the sample variance, and we'll see that the sample variance is expected value is the actual variance of that underlying variable. So let's prove this, and then we'll stop for today. The proof is somewhat involved in all algebra, but let's see that. So for instance, the sum of these variables is the same as n times the sample mean, because the sample mean is the sum of variance divided by x. And we notice that this term that appears here, we are going to need to talk about this term that appears here. That term can be rephrased as each xi deviates from the actual expected value, and then the sample average or the sample mean deviates from the actual expected value. Because even though the expected value of this is that, and the expected value of this is that, then this usually deviates more than this. We're going to need this. And we have this here. This is kind of a estimate for that, but it's got an error that depends on how big the error is for the sample mean, because the sample mean itself is not absolutely the expected value. Turns out that's why we have this divisor n-1 here. And it's simply algebra. This, terrible. So let's look at the expected value here. So here, we have the formula here. So that's the expected value. We can take this n-1 over n-1 as a multiplier here. So we'll take it shortly. We replace first this by this our estimate. So this is the xi minus mu, and this is the x bar minus mu here to denote that this, oh, there's another missing parenthesis there. Sorry. I'll have to fix that. Let's see. We're a little bit on overtime, but what? Did I not fix it? Did I put it in the wrong place? Didn't I? Oh, I put it in the wrong place. Oh, sorry. It should be there. Now, that's better. Yeah, now it's better. Then we multiply this thing here wide open. We blow it open. So there's this xi minus mu minus 2 times xi minus mu. There should be parentheses here to denote this. Everything is being summed, plus x bar minus mu. So I rewrite this again. This one is separated as a separate sum. This one is separated as a separate sum. This middle one, this is now doesn't depend on xi, so it becomes a multiplier, and then we're adding these. And then this one is added to itself n times, so it's simply n times that. And here, this sum, in every step of the way we subtract mu, so it's in fact just n times, this added here, it's just n times this minus n times mu. And here we have still that. And this is the sum. But we notice here that this sum here, oh, sorry. This sum here and this sum here, we can rewrite it as the expected value of this minus the expected value of this. And then here, this is the expected value of xi minus mu squared, but each and every one of these expected values is in fact the variance of xi. And here, xi minus mu squared expected value is the variance of this x bar. This x bar minus here, x bar minus mu squared, that's the variance of x bar. But we derived that variance to be sigma squared over n, and we're doing this n times over, so it's n times sigma squared over n. So this becomes a sigma. This is n times the variance of xi. So it's n times sigma squared. So n times sigma squared minus sigma squared, that's n minus 1 times sigma squared. And that's why we divide this by n minus 1, and we get sigma squared here. So, I mean, this is not the sort of proof and algebraic prowess that I expect you to display here, but I just thought that for completeness sake and for understanding that there's nothing magical going on here, it's just a little bit complicated algebra that we have to do to show that the expected value is in fact sigma squared. But it justifies to you why we need this dividing over 1 over n minus, multiplying with 1 over n minus 1 is instead of n, which you might intuitively expect. Okay. Now we're going to conclude for today. I'm going to stop the recording and we'll reconvene tomorrow. If you have any questions, you can ask